Tonight we're going to fall into the most terrifying object in the known universe. Not metaphorically, not as a thought experiment. We're going to follow a journey, step by step, into a place where space itself ends, where time loses all meaning, and where the laws of physics that govern every single moment of your life simply cease to exist. A place that swallows light. A place that swallows everything. And tonight, before you sleep, you're going to understand exactly what that means. Here is the thing most people don't realize. A black hole is not a hole. It is not empty. It is not dark in the way a room is dark when you turn off the lights. A black hole is a place where matter has been compressed with such unimaginable violence, crushed with such impossible force, that it has torn a wound in the fabric of reality itself. At its center lies something called a singularity, a point of infinite density, infinite gravity, a place where our best equations, the ones that describe everything from the orbit of planets to the glow of distant stars, break down completely and return nothing but meaningless infinities. We do not know what happens there. No one does. And that silence, that gap in our understanding is perhaps the most terrifying thing of all. By the end of tonight, you're going to understand exactly why falling into a black hole is nothing like what the movies have shown you. You're going to understand what you would see, what you would feel, and when, precisely, the point of no return would arrive. You're going to understand why time itself would betray you, why the universe outside would age billions of years in what feels to you like moments, why a friend watching from a safe distance would never see you cross the threshold at all. You would simply slow, and freeze, and dim, and vanish, and they would never know what happened next, but you would. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Tonight, we are going to do something that no human being has ever done. We are going to fall into a black hole, not in a spacecraft, not protected by any technology. We are going to follow the journey as physics describes it, step by step, moment by moment, from the first instant you begin to fall, all the way to the end. And I want you to understand something before we go any further. The end is not what you think it is. I want you to get comfortable right now. If you are lying down, let your body settle. If you're sitting, let your shoulders drop. Because what we are about to explore together is one of the most profound and unsettling journeys the human mind has ever attempted to map. Not because it is violent, not because it is loud, but because it is quiet in the most terrifying way imaginable. A black hole does not roar. It does not announce itself. It simply waits. And everything that comes close enough simply never leaves. Here is the thing most people do not realize when they first hear the words black hole. They picture a void, a vacuum, a dark tunnel spinning in space. And yes, in a sense there is darkness involved. But a black hole is not a hole in the way we understand holes. It is not absence. It is the opposite. It is an almost incomprehensible concentration of presence, of mass, of gravity so extreme that it has done something that should be impossible. It has bent the geometry of space and time into a shape from which there is no return. Not for matter, not for light, not for anything. The numbers involved are almost impossible to hold in your mind. And I say almost because tonight we are going to try. The black hole at the center of our own galaxy, the one astronomers call Sagittarius A star, contains the mass of 4 million suns, 4 million, compressed into a region of space smaller than the distance between the Earth and the Sun. And that is considered a modest black hole by cosmic standards. There are black holes out there in the universe that contain the mass of 66 billion suns. 66 billion! Objects so massive that if you placed one at the center of our solar system, its event horizon, the boundary of no return, would stretch out past the orbit of Neptune. And yet, if you were falling toward one of those giants, you might not feel a thing as you crossed that threshold. No alarm, no wall, no warning, just one moment on the outside of everything, and the next moment inside, with no way back, ever. That idea, that quiet, invisible, irreversible crossing, is what I want us to sit with tonight. Because I think it is one of the most philosophically stunning things that physics has ever revealed to us. Before we go deeper, let me tell you what tonight is really about. It is not just about the physics, though the physics is extraordinary. It is about perspective. It is about what black holes reveal to us about the nature of reality itself. about time, about information, about what it means for something to exist, and then apparently not to exist anymore. These are questions that the greatest minds in science are still wrestling with. Questions that Einstein's equations opened but could not close. Questions that Stephen Hawking spent decades circling, and questions that, in a strange and beautiful way, remind us how small and how remarkable we are for even being able to ask them. Picture the universe as it was roughly 10 billion years ago. A young cosmos dense with gas and dust, galaxies still taking shape, stars being born and dying at a furious rate. In the heart of a massive star, maybe 50 times the mass of our own sun, something is about to happen. A core collapse. A death so violent it briefly outshines the entire galaxy around it. And from that death, from that implosion of unimaginable force, something new is born. Something that will persist for longer than the current age of the universe. Something that warps the space around it like a bowling ball pressed into a rubber sheet, pulling everything nearby toward its center, never releasing its grip. A black hole enters the universe, and the universe will never be quite the same. That image, that birth from death, that permanence born from violence, is one of the things I find most haunting about black holes. They are not anomalies, they are not glitches in the universe. They are a natural consequence of the rules that govern everything. Given enough mass, given enough gravity, given enough time, collapse is inevitable. And in a way, that applies to far more than just stars. It is a reminder that the universe has a direction. Things move, they burn, they collapse, they transform. Nothing stays the same forever, not even the stars. Now, I want to be honest with you about something. There is a great deal that we do not know about black holes. In fact, some of what we think we know is actively contested by physicists right now. There is a paradox at the heart of black hole science, so deep and so troubling that it has divided some of the greatest thinkers in modern physics for decades. It involves quantum mechanics on one side and general relativity on the other. Two theories that each work perfectly in their own domain. Two theories that, at a black hole's boundary, flatly contradict each other. And nobody has yet figured out how to reconcile them. That contradiction, that crack in our understanding of reality, is something we are going to explore together tonight. But let us not get ahead of ourselves. Tonight, we fall. Slowly, carefully, one layer at a time. We begin with what a black hole is and how it forms. We move to the edge, to that invisible threshold called the event horizon, and we explore what it actually means to cross it. We talk about time, about light, about what an outside observer would see as you fell, and about what you yourself would experience in those final moments. We talk about the firewall, about Hawking radiation, about the information paradox, and at the end we pull back. We look at this from the widest possible angle, and I think, if we do this right, you're going to come away from tonight not just knowing more about black holes, but feeling something. A kind of awe that is also, quietly, a little terrifying. That is the gift that the universe offers us when we look honestly at its most extreme places. It does not comfort us with easy answers. It opens a door and says, look at this. Look at how strange and vast and deep reality actually is. And somehow in that strangeness, there is a kind of peace. A reminder that the questions themselves are worth holding, that not knowing is not a failure. It is the beginning of everything. So settle in. Let the night be quiet around you. Let whatever you are carrying today begin to loosen its hold. Because tonight, for a little while, we are going to let the universe be as big as it actually is, and we are going to fall, together, into the dark. Let me ask you something. When you think of the word hole, what do you picture? A gap, an opening, an absence of something that was there before. A hole in the ground, a hole in a wall, a hole in a piece of paper. A hole is defined by what is not there, by emptiness, by the space left behind when something is removed. And that is precisely why the name black hole is one of the most misleading phrases in all of science. Because a black hole is not empty. It is not an absence. It is, in the most literal sense possible, the opposite. A black hole is what happens when matter becomes so dense, so impossibly concentrated, that it stops behaving the way matter is supposed to behave. Normally, if you compress something, it resists. Squeeze a ball of gas, and the pressure builds until it pushes back. Compress a solid, and its atomic structure fights back against the force. The atoms themselves, their electrons, their quantum nature, resist further compression with a stubbornness built into the fabric of physics. But there is a threshold, a point beyond which that resistance fails, beyond which nothing, not pressure, not quantum mechanics, not the repulsive force between particles can stop the collapse. And when that threshold is crossed, something extraordinary and terrible happens. The matter does not just compress, it collapses all the way, down to a point, a mathematical point with no width, no height, no depth, infinite density, infinite gravity, a singularity. The word singularity comes from mathematics, and it means a point where an equation breaks down, where you divide by zero, where the answer becomes infinite, which in mathematics is another way of saying the answer stops making sense. When physicists calculate what happens at the center of a black hole using Einstein's equations of general relativity, those equations return infinities. Not very large numbers, not approximations, actual infinities. And in physics, when your equation returns infinity, it does not mean the answer is infinitely large. It means your equation has stopped working. It means the theory, no matter how brilliant it is, no matter how well it describes everything else in the universe, has hit a wall, has encountered something it was not built to describe. The singularity is not just a strange place in space, it is the edge of our understanding of reality itself. Now, I want you to picture something with me. Picture the fabric of space as a flat rubber sheet, stretched tight in all directions. You place a heavy ball on that sheet and it sinks. It creates a depression, a curve, a well. Everything nearby begins to roll toward it. The heavier the ball, the deeper the well, the steeper the slope, the faster things roll in. This is essentially how gravity works in Einstein's framework. Massive objects do not just pull on other objects through some invisible force. They curve the space around them, and other objects follow those curves. This is why the Earth orbits the Sun. Not because the Sun reaches out and grabs it, but because the Sun has curved the space around it so deeply that the Earth's natural path through that curved space traces an ellipse. Now take that heavy ball on the rubber sheet and make it heavier. Heavier and heavier and heavier. The depression gets deeper. The slope gets steeper. Objects nearby have to move faster and faster just to avoid sliding in. At some point the ball becomes so heavy that the sheet does not just dip. It punctures. It tears. The well becomes infinitely deep, infinitely steep, and anything that gets close enough can no longer escape no matter how fast it moves. Not even if it moves at the speed of light. And light, as far as we know, is the fastest thing that exists. There is no faster. There is nothing that could outrun the gravity of a singularity once it has you within a certain distance. That distance is the event horizon, and we will spend a great deal of time there tonight. But here is what I want to sit with for a moment. The singularity at the heart of a black hole is not just extreme. It is a place where the concept of place itself becomes unstable. Space and time, as we understand them, are not separate things. Einstein showed us that they are woven together into a single fabric called space-time. And near a singularity, that fabric does not just bend. It does not just stretch. It reaches a condition that our mathematics cannot describe and our intuition cannot follow. Some physicists believe the singularity is a real physical thing, a genuine point of infinite density sitting at the center of a black hole. Others believe the singularity is a signal, a placeholder, a gap in our theory where a better theory, one that unites general relativity with quantum mechanics, would give a finite, sensible answer. We do not yet have that better theory. We're still looking for it. Here is the thing most people do not realize about black holes. They are not rare. They are not exotic exceptions to the rules of the universe. They are, in a very real sense, inevitable. The universe makes them constantly. Every time a star massive enough reaches the end of its life and its core collapses, the conditions for a black hole are met. And the universe has been making stars and killing stars for nearly 14 billion years. There are estimated to be somewhere between 100 million and 1 billion stellar mass black holes in the Milky Way alone. Our galaxy, the one we live in, is full of them. They drift through space unseen, warping the light of distant stars, occasionally pulling in gas or dust and briefly announcing their presence with a faint glow. But mostly they are silent, invisible, patient. And then there are the giants, the supermassive black holes that sit at the centers of most large galaxies, including our own. These are not formed the same way as stellar black holes, at least not entirely. Their origin is one of the open questions of modern astrophysics. But their existence is beyond doubt. We have imaged one. In 2019, the Event Horizon Telescope produced the first direct image of a black hole, the one at the centre of a galaxy called Messier 87, 530 million light-years from Earth. Its mass is 6.5 billion times the mass of our Sun, 6.5 billion, and its event horizon is so large that our entire solar system would fit comfortably inside it. I want you to let that settle for a moment. 6.5 billion solar masses, a boundary of no return large enough to swallow our Sun, our planets, every comet and asteroid and moon in our cosmic neighbourhood, and still have room left over. This object exists. We have seen it. We have photographed the glow of superheated gas orbiting its edge at a significant fraction of the speed of light. It is not theoretical. It is not a model. It is out there, in the dark between galaxies, and it has been there for billions of years, and it will be there for billions more. And yet, for all of that immensity, for all of that gravitational dominance, a black hole is also, in a strange way, simple. Simpler than almost any other object in the universe. Because once matter crosses the event horizon, all the complexity it carried, its temperature, its chemical composition, its shape, its history, seems to vanish. A black hole, according to the equations we have, is described completely by just 3 numbers: its mass, its electric charge, and its spin. That is it. 3 numbers. Physicists call this the no-hair theorem, meaning a black hole has no distinguishing features beyond those 3 quantities. Everything else is erased. And that erasure, that apparent destruction of information, is one of the deepest and most troubling problems in all of modern physics. We will return to it. But for now, I want you to hold this image. A darkness that should not exist. A point where the laws of nature reach their limit. A place that is not empty, but is the most full thing imaginable. That is a black hole. And we're only just beginning to understand what it means to fall toward one. To understand what a black hole is, you first have to understand what it was before. Because black holes do not appear from nothing. They are not born from emptiness. They are born from something that was, for millions of years, one of the most luminous and powerful objects in the universe. They are born from the death of a star. And the death of a star is one of the most violent events that the cosmos is capable of producing. Let us start with the Sun. Our Sun. The warm, steady presence that has governed every single day of your life, that has driven every weather system, every ocean current, every photosynthetic reaction that ever produced the food you have eaten. The Sun is, by any human measure, enormous. Its diameter is about 109 times the diameter of the Earth. You could fit 1,300,000 Earths inside it. It burns at a surface temperature of roughly 5,500 degrees Celsius, and at its core the temperature reaches 15 million degrees. It has been burning for about 4.6 billion years, and it will continue to burn for roughly another 5 billion years before it begins to die. But here is the thing about the Sun. In the grand hierarchy of stars, our Sun is average, modest even. A quiet, stable, medium-sized star doing what medium-sized stars do. There are stars out there that make our Sun look like a candle flame next to a bonfire. The stars that create black holes are the massive ones. Stars born with masses roughly 20 to 30 times that of our Sun, or more. These are the giants, the hypergiants, the blazing blue and white behemoths that burn so ferociously that they consume their fuel in millions of years rather than billions. Where our Sun is a slow, steady fire lasting 10 billion years, a star of 30 solar masses burns so intensely that it exhausts itself in perhaps 3 million years, a cosmic eye blink. These stars are extravagant and brief, pouring out energy at a rate millions of times greater than our Sun, and living short, spectacular lives that always end the same way. The engine that powers every star is nuclear fusion. In the core, under the crushing weight of the star's own gravity, hydrogen atoms are squeezed together so tightly and heated so ferociously that they fuse. 4 hydrogen nuclei merge into one helium nucleus, and in that merging, a tiny amount of mass is converted directly into energy. This is Einstein's most famous equation at work. That energy radiates outward, producing the pressure that pushes back against gravity. And this balance, the inward pull of gravity against the outward push of fusion energy, is what keeps a star alive. It is what gives a star its size, its shape, its stability. As long as fusion continues, the star holds itself up. The moment fusion fails, gravity wins. For a massive star, the fusion process is a race through the periodic table. It begins with hydrogen. When the hydrogen in the core is exhausted, the core contracts and heats further until helium begins to fuse into carbon. When the helium is gone, carbon fuses into neon, then oxygen, then silicon. Each stage is shorter than the last, because each stage releases less energy per reaction. The final stage, silicon fusing into iron, lasts only a matter of days, and then comes iron. Iron is the end of the road. Fusing iron does not release energy, it consumes it. The moment an iron core begins to accumulate at the heart of a massive star, a clock starts ticking, and it counts down very, very fast. When the iron core reaches approximately 1.4 times the mass of our Sun, something extraordinary happens. The pressure that quantum mechanics provides, the resistance of electrons to being squeezed together, can no longer support the core against gravity. The core collapses, not slowly, not gradually. In less than 1 second, a core the size of Earth, roughly 12,000 kilometers across, collapses into a sphere roughly 20 kilometers across. 20 kilometers. The density becomes so extreme that atomic nuclei are crushed together, protons and electrons merging into neutrons, and the collapse is halted briefly by the resistance of neutron matter. The core bounces, and that bounce sends a shock wave outward through the rest of the star at a significant fraction of the speed of light. What follows is a supernova. The outer layers of the star, everything above that collapsed core, are blasted outward in an explosion so energetic that it briefly outshines the entire galaxy it lives in. Every single star in a galaxy of hundreds of billions of stars, and for a few weeks, one dying star outshines all of them combined. The energy released in a supernova in the form of light, heat, and kinetic force is almost beyond description. But here is something that will genuinely stop you: the visible light, the spectacular explosion that astronomers can see across billions of light years. That is only about 1% of the total energy released. The other 99% is carried away in a single second by a flood of particles called neutrinos. Particles so small and so weakly interacting that they pass through the entire body of the star as if it were not there. In that 1 second, more energy is released than our Sun will produce in its entire 10 billion year lifetime. And what is left behind? If the collapsing core has enough mass, if the star was large enough, the neutron matter itself cannot hold. The collapse continues, and now there is nothing left to stop it. No pressure, no quantum resistance, no force in known physics that can push back. The core collapses all the way to a singularity. A black hole is born. It emerges from the wreckage of a star that burned for millions of years, that forged inside its core every heavy element you will ever encounter, from the carbon in your body to the iron in your blood, and that ended its life in a single catastrophic second of implosion followed by a titanic explosion. The black hole is what remains after all of that fury, silent, dark, impossibly small and impossibly dense, patient in a way that only something with essentially infinite time can be patient. There is something I find deeply moving about this sequence of events. The star does not simply disappear, it transforms, it distributes itself. The outer layers, blown into space by the supernova, seed the surrounding region with heavy elements. Those elements drift and accumulate over millions of years, mixing with hydrogen clouds until gravity pulls them together again and a new generation of stars is born. Stars that may have planets, planets that may have oceans and atmospheres, and, eventually, life. The iron in your blood was forged in the heart of a dying star. The calcium in your bones was scattered into space by a supernova. You're not separate from this process, you're a continuation of it, and at the center of all of that transformation, all of that cosmic recycling, sits the black hole, the remnant, the leftover, the thing that could not be scattered or dispersed or transformed into something else, the thing that simply remained, collapsed beyond the point of return, sealed behind an event horizon, cut off from the rest of the universe by the very extremity of its own gravity. It will persist long after the stars it was born among have themselves grown old and died. Long after the galaxy around it has changed beyond recognition, the black hole endures, because once formed, a black hole's existence is, for all practical purposes, permanent, at least on any timescale that matters to a human mind lying in the dark, listening to the night, and wondering what is really out there. There is a boundary in space that has no physical surface, no wall, no fence, no visible marker of any kind. You could pass through it without feeling a single thing, without seeing a flash of light or hearing a sound or sensing any change in the air around you. And yet, the moment you cross it, your fate is sealed in the most absolute way that physics allows. You will never return. You will never send a message back. You will never be seen again by anyone on the other side. That boundary has a name. It is called the event horizon, and it is, without question, one of the most haunting concepts in all of science. The name itself tells you something important. An event horizon is a horizon of events. Think about the horizon you see when you stand at the edge of the ocean and look out at the water. Beyond a certain distance, you cannot see what is happening. Ships disappear over it. The curvature of the Earth hides them from view, but they still exist. They are still out there. Someone on that ship could, in principle, turn around and come back. The event horizon of a black hole is different in a way that goes far deeper than mere distance. Events that happen beyond a black hole's event horizon are not just hidden from outside observers because of distance or curvature. They are permanently, irreversibly cut off. No signal, no light, no particle, no information of any kind can travel from inside the event horizon to outside it. What happens inside is not just hidden, it is causally disconnected from the rest of the universe. The concept of the event horizon follows directly from a simple question that physicists began asking in the early 20th century. If gravity is strong enough to curve the path of light, can it ever be strong enough to stop light entirely? Albert Einstein's general theory of relativity, published in 1915, gave physicists the tools to answer that question. And within months, a German physicist named Karl Schwarzschild, writing from the trenches of the First World War, had found an exact solution to Einstein's equations that described the geometry of space around a perfectly spherical, non-rotating mass. That solution contained something strange. At a certain distance from the centre of any sufficiently compressed mass, the equations predicted a surface where time, as seen from the outside, appeared to stop entirely, where the escape velocity, the speed you would need to travel to pull free of gravity, equaled the speed of light. Schwarzschild called it a peculiarity. Today we call it the Schwarzschild radius, and the sphere defined by that radius around any mass is the event horizon. Here is the thing most people do not realize about escape velocity. Escape velocity is not a wall. It is a threshold for unpowered objects. If you fire a rocket upward from the surface of the Earth, you need to reach roughly 11 kilometers per second to escape Earth's gravity without any further thrust. But you could, in principle, escape at any speed, as long as you kept your engines burning. Climb slowly enough, and you can still get away, as long as you never stop. Near a black hole's event horizon, that loophole closes. The curvature of space-time becomes so extreme that every direction, including what you would normally call upward, bends back toward the singularity. It is not that you cannot go fast enough, it is that the geometry of space itself has been warped so severely that there is no path that leads away. Every path leads inward. To escape, you would need to travel faster than light in a universe where nothing travels faster than light. It is not a practical limitation, it is a fundamental one. Let us talk about the size of an event horizon, because the numbers are extraordinary. The Schwarzschild radius of any object is proportional to its mass. For an object with the mass of our Sun, the Schwarzschild radius is approximately 3 kilometers. That means, if you could compress our entire Sun, all of it, every last atom of its 1.99 times 10 to the power of 30 kilograms of mass, into a sphere 3 kilometers across, the surface of that sphere would be the event horizon of the resulting black hole. 3 kilometers. You could drive that distance in a few minutes on a highway. For the Earth, the Schwarzschild radius is even more striking. You would need to compress all of Earth's mass into a sphere roughly 9 millimeters across, the size of a marble containing everything that Earth is, and that marble would be a black hole. Everything outside that 9 millimeter radius would be free. Everything inside would be forever trapped. For supermassive black holes, the event horizons become almost incomprehensibly large. The black hole at the center of Messier 87, the one we photographed in 2019, has an event horizon with a radius of roughly 20 billion kilometers. 20 billion kilometers, Our entire solar system from the Sun to the orbit of Neptune spans about 30 billion kilometers, so the event horizon of that single black hole is more than half the width of our solar system. If you replaced our Sun with that black hole, the event horizon would reach more than halfway to Neptune. Everything inside that boundary, every orbit, every planet, every moon, would be inside the point of no return. And here is the detail that I think is the most quietly terrifying of all. The event horizon is not a physical surface. There is nothing there. No membrane, no glow, no resistance. If you were falling toward a large enough black hole, you would pass through the event horizon without any sensation whatsoever. No alarm would sound, no force would push back against you. The stars around you would look strange, distorted by the gravitational lensing of the black hole, but you would still see them. You would still feel weightless in free fall. You would have no direct, immediate way of knowing that you had just crossed the most significant threshold in the universe. Only later, as you tried to change course, as you tried to fire engines to push yourself away, as you watched the singularity grow inevitable before you, would the reality of what had happened become clear. You crossed the line, and you did not even feel it. This is what makes the event horizon so philosophically unsettling. We are accustomed to boundaries being marked. A door, a wall, a cliff edge. The things that separate safety from danger usually announce themselves. The event horizon is the ultimate exception. It is a point of no return that you can cross in perfect comfort, in perfect ignorance, and only discover afterward. And by afterward, I mean in the time remaining before the singularity, which, depending on the size of the black hole, could range from microseconds to hours. You're inside, you're falling, and the universe outside has already, in every physical sense that matters, let you go. There is one more thing I want to tell you about the event horizon before we go further. From the outside, from the perspective of someone watching you fall in, you never actually cross it. General relativity tells us that time runs slower, in stronger gravitational fields, and the gravitational field near the event horizon is so extreme that, to a distant observer, time for the infalling person appears to slow to a crawl and then stop entirely. The outside observer would see you approach the event horizon and then appear to freeze there, growing dimmer and redder as the light from your body is stretched by gravity, until you fade entirely from view. You would never appear to cross. You would simply become a ghost at the edge, a shadow on the boundary, forever, as far as the outside universe is concerned. But from your own perspective, from inside your own experience, you would cross, you would fall through. And what awaits you on the other side is something that the universe has kept hidden from every observer who has ever lived. Until now, as we go deeper together into the dark, close your eyes for a moment and picture space as most of us imagine it. Dark, quiet. A vast black canvas scattered with the cold light of distant stars, each one a steady, unwavering point of white against the infinite dark. Now imagine that somewhere ahead of you there is a black hole. Not close enough yet to be dangerous, just close enough to see. What do you think you would see? A sphere of absolute darkness, a swirling drain, a tear in the fabric of space? The reality is stranger and more beautiful and more terrifying than almost any of those images, and tonight I want to walk you through exactly what your eyes would encounter as you fell toward one. Let us start far out, at a safe distance. If you were approaching a black hole that existed in isolation, with no surrounding gas or dust, the first thing you would notice is not darkness, it would be distortion. The black hole's gravity bends the path of light travelling near it, a phenomenon called gravitational lensing. Light from stars behind the black hole gets deflected around it, following the curves of warped space-time, and arrives at your eyes from angles that seem impossible. Stars that should be hidden behind the black hole appear around its edges, smeared and stretched into arcs. Stars that should be in completely different parts of the sky get pulled and twisted toward the dark center. The entire background of the universe around you becomes a warped, luminous ring, a halo of distorted starlight wrapped around a sphere of nothing. It is one of the most visually extraordinary things that general relativity predicts, and it is real. We have observed gravitational lensing around massive objects across the universe, at the very edge of the black hole's shadow, where the warping of light becomes most extreme. There is something called the photon sphere. This is a region sitting at 1.5 times the Schwarzschild radius outside the event horizon, where light itself can travel in circles. Photons moving at the speed of light can in principle orbit a black hole at this distance indefinitely, looping around and around in a ring. It is a razor-thin zone where the geometry of space forces light into a closed path. If you were positioned exactly at the photon sphere, you could in theory see the back of your own head by looking forward, because light from it would have travelled all the way around the black hole and returned to your eyes. That image, the idea of a place where vision curves back on itself, where forward and backward become the same direction for a beam of light, is one of the moments where reality stops feeling like physics and starts feeling like something else entirely. Now add an accretion disk. Most black holes that we observe in the universe are not isolated. They are surrounded by vast, swirling structures of gas and dust and superheated plasma, material that has been drawn in from nearby stars or gas clouds and that spirals slowly inward like water circling a drain. This structure is called an accretion disk, and it is nothing like the calm glowing rings you might have seen in artistic renderings. An accretion disk is a sight of extraordinary violence. The material within it is compressed and heated by friction and magnetic forces to temperatures of millions of degrees. It radiates across the entire electromagnetic spectrum, from radio waves to visible light to X-rays. The innermost regions of an accretion disk around a stellar mass black hole can outshine an entire star. Around a supermassive black hole, the accretion disk can outshine an entire galaxy. These structures, called quasars when they are at their most luminous, are the brightest sustained phenomena in the known universe, and they are powered entirely by matter falling into a black hole. So here is the paradox that I find most striking about black holes. We call them black. We define them by the fact that no light escapes them. And yet, a black hole actively feeding on surrounding matter is one of the most luminous objects in existence. The darkness at the centre is surrounded by a blazing halo of light so intense it is lethal at close range. The most light-devouring object in the universe is also, indirectly, one of the most radiant. It is a contradiction that captures something essential about the way the cosmos works. Extremes breed extremes. The deepest darkness generates the most ferocious light. As you fall closer, the visual effects become increasingly dramatic. The gravitational lensing intensifies. The photon ring around the black hole's shadow grows brighter and more defined. The accretion disk, if one is present, begins to look asymmetric in a way that seems wrong at first glance. One side of the disk appears far brighter than the other. This is not an illusion. It is a real effect called relativistic beaming. The material in the accretion disk is orbiting the black hole at a significant fraction of the speed of light. On the side where the disk is moving toward you, the light from the material is blue-shifted and amplified, appearing brighter and more energetic. On the side moving away, the light is red-shifted and dimmed. The disk appears to glow unevenly, one arc blazing and the other fading, a visual signature of matter moving at relativistic speeds around an object of incomprehensible density. The black hole's shadow itself, the region of sky that appears completely dark because all the light paths leading there terminate at the singularity, is not perfectly circular if the black hole is spinning. Most black holes we know of are spinning, some at rates close to the maximum allowed by physics. A rapidly spinning black hole drags space-time itself around with it, in a process called frame dragging, twisting the fabric of space in the direction of its rotation. This warps the shadow into a slightly asymmetric shape, and shifts the photon ring off-center in subtle ways that depend on the spin rate and the viewing angle. The image produced by the Event Horizon Telescope in 2019 captured exactly this structure around Messier 87's central black hole, a bright, slightly asymmetric ring of light around a dark central shadow. It matched the predictions of general relativity with remarkable precision. And then there is the light from the stars. As you fall inward, the distribution of starlight around you shifts. Because of the gravitational lensing effect growing stronger, more and more of the light from the entire universe appears to concentrate in a shrinking ring ahead of you, surrounding the black hole's shadow. The universe behind you appears to compress into a smaller and smaller circle of light at your back, while ahead of you the darkness grows. The ring of distorted starlight tightens, the black hole's shadow expands until it fills your entire forward view, and then, as you approach the event horizon, the ring of starlight narrows to almost nothing, and the darkness ahead is total. Not the darkness of a room at night, not the darkness of deep space, a different kind of darkness, a darkness that means an ending, a darkness that means you have arrived at the place where light itself has run out of a road. You have not crossed the event horizon yet, not quite, but you are at the edge of it, and everything you have just seen, the distorted stars, the blazing accretion disk, the twisting photon ring, the expanding shadow, has been the universe's way of showing you what it looks like to approach the ultimate boundary. A visual symphony of warped light and relativistic physics, growing more extreme with every kilometre of your descent. What comes next, what happens when you actually cross, is where the physics becomes something even stranger. Something that bends not just light, but time itself. I want you to think about time for a moment. Not as a concept, not as something measured by clocks and calendars, but as a physical thing. Something real. Something that exists in the universe the way matter and energy exist. Because that is what Einstein told us time actually is. Not a backdrop, not a stage on which events occur, but a dimension woven together with the 3 dimensions of space into a single fabric called space-time. And like any physical thing, that fabric can be stretched, it can be compressed, it can be warped by the presence of mass and energy. And near a black hole, it is warped more severely than anywhere else in the known universe. Near a black hole, time itself begins to break. The idea that gravity affects time is one of the most counterintuitive predictions of general relativity. When Einstein first proposed it in 1915, it seemed almost too strange to be taken seriously. We experience time as constant. A second feels like a second. An hour feels like an hour. The rhythm of our lives is built on the assumption that time ticks forward at a steady, universal rate, the same for everyone, everywhere. Einstein said that assumption is wrong. Time does not tick at a universal rate. It ticks differently depending on where you are in a gravitational field. The stronger the gravity, the slower time passes. Not as an illusion, not as a perceptual trick, as a real, measurable, physical fact. We have verified this on Earth. The clocks aboard GPS satellites, orbiting high above the planet where Earth's gravity is weaker, tick slightly faster than clocks on the ground. If engineers did not correct for this effect, every GPS system on the planet would accumulate errors of several kilometres per day. The correction is small, a matter of microseconds. But it is real, and it is necessary, and it confirms what Einstein predicted. Gravity slows time. The deeper you are in a gravitational well, the slower your clock runs relative to someone higher up. Now take that effect and scale it to the gravity of a black hole. Scale it to the most extreme gravitational environment the universe can produce. And time does not just slow slightly. Time, as experienced by an outside observer watching someone fall in, appears to stop entirely at the event horizon. Here is how to picture it. Imagine you are watching a friend fall toward a black hole from a safe distance. You watch them drift closer and closer to the event horizon. As they fall, the light they emit, the photons bouncing off them and travelling to your eyes, has to climb out of an increasingly deep gravitational well to reach you. And as those photons climb, they lose energy. Their wavelength stretches. They shift toward the red end of the spectrum, a phenomenon called gravitational redshift. Your friend begins to appear redder, dimmer, and simultaneously, the time between each photon reaching your eyes grows longer, because each successive photon has to climb from slightly deeper in the gravitational field. The images of your friend arrive at your eyes more and more slowly. Their movements appear to slow. Their clock, as you observe it, begins to tick more and more leisurely. And as they approach the event horizon itself, this effect reaches its logical extreme. The photons from the moment of crossing take, in principle, an infinite amount of your time to reach you. Your friend appears to freeze at the edge. Their image grows redder and redder, dimmer and dimmer until it fades entirely from view. They never appear to cross. They simply become a ghost, a fading echo at the boundary, and then nothing. But here is the thing that makes this so terrifying and so strange. From your friend's perspective, none of that happened. They did not freeze, they did not slow, they did not fade, they fell. In their own experience of time, the crossing of the event horizon took whatever it took. Perhaps seconds, perhaps minutes, depending on the size of the black hole, and it was ordinary. Their heartbeat did not slow, Their thoughts did not stretch. They experienced time the way they always have, as a continuous forward-moving flow. The slowing was not something they felt. It was something only you saw from the outside, because of the way gravity distorted the light carrying information between you. Two entirely different realities, both physically valid, both described correctly by general relativity, unfolding simultaneously for two observers sharing the same event. This is one of the places where relativity stops being an abstract theory and starts feeling genuinely disorienting. There is no single universal answer to the question of when your friend crossed the event horizon. From your perspective, they never did. From theirs, they already have. Both answers are correct within their own reference frames. General relativity does not give you a God's-eye view of the universe where there is one true timeline everyone shares. It gives each observer their own valid timeline, shaped by their motion and their position in a gravitational field. Near a black hole, those timelines diverge so dramatically that what is a moment for one person is an eternity for another. Now I want to take this even further. Because the time dilation near a black hole is not just a perceptual oddity, it has real consequences for what an infalling observer experiences in their final moments. As you fall toward a stellar mass black hole, the tidal forces, which we will explore in the next chapter, would destroy you long before you reach the event horizon. But for a supermassive black hole, where the tidal forces at the horizon are gentler, you would cross freely. And in the time between crossing the event horizon and reaching the singularity, something extraordinary happens to the nature of time itself inside the black hole. Physicists describe it this way. Inside the event horizon, the radial direction toward the singularity ceases to be a direction in space and becomes instead a direction in time. You cannot avoid moving toward the singularity for the same reason you cannot avoid moving into the future. It is not a location you are falling toward. It is a moment you cannot escape. Your future, inside a black hole, is not a place. It is a time, and it is coming toward you whether you move or not. Let me give you an analogy that I find both clarifying and quietly haunting. Imagine you are on a river. At first, the current is gentle, and you can swim in any direction you choose. You can move upstream, downstream, sideways. You have freedom of movement in all directions. But as you approach a waterfall, the current accelerates. Progressively, your ability to swim upstream diminishes. The current is too strong. At some point, every direction of swimming still carries you toward the edge. The fall becomes inevitable, not because a wall has blocked you, but because the medium you are moving through has taken on a direction of its own. Inside a black hole, space-time itself has taken on a direction, and that direction is the singularity. Time flows you toward it, the way a river flows toward a waterfall, and there is no swimming fast enough to reverse course. And yet, knowing all of this, there is something almost meditative about it. We spend so much of our lives fighting time, wishing we had more of it, grieving its passage, resenting the way it moves only forward and never lets us go back. A black hole takes that relationship with time and makes it visible in a way that nothing else in the universe does. It shows us that time is not a given. It is a feature of the geometry of space. It bends around mass. It slows in the presence of gravity. It can, at the extremes of reality, stop being a dimension of freedom and become a dimension of inevitability. In that sense, a black hole does not just warp time, it reveals it, strips away the comfortable illusion that time is a steady, neutral river, and shows us what it actually is. A dimension of the cosmos, as wild and as malleable as space itself. And in the dark, lying still, breathing slowly, there is something almost peaceful about that truth. There is a word that physicists use to describe what happens to matter that falls too close to a black hole. It is not a word you would normally expect to find in a scientific paper. It is not clinical or abstract or Latin-derived. It is, in fact, a word that sounds almost playful, almost absurd, until you understand what it actually describes. The word is spaghettification, and what it describes is the process by which a black hole's tidal forces stretch any infalling object, any rock, any spacecraft, any human body, into a long, thin strand of matter. Like pasta, like a noodle drawn out by invisible hands pulling in opposite directions, with a force that no material in the universe can resist. It is one of the most visceral and specific things that physics predicts about black holes. and it is real. To understand spaghettification, you first need to understand tidal forces. You already know about tides. The ocean tides on Earth are caused by the moon's gravity, but the moon does not pull on the entire Earth equally. It pulls slightly harder on the side of Earth closest to it, and slightly less hard on the side farthest from it. This difference in gravitational pull across the diameter of the Earth is what creates the tidal bulge. The oceans on the near side are pulled toward the moon a little more than the solid Earth beneath them, and the oceans on the far side are pulled a little less, so they bulge outward in the opposite direction. Two tidal bulges, one facing the moon, one facing away. This is why there are two high tides per day as the Earth rotates. The moon's gravity is not uniform across our planet, and that non-uniformity creates a stretching force. Now scale that concept up, dramatically. Near a black hole, the gradient of gravity, the difference in gravitational pull between the near side and the far side of any object, becomes extreme. If you were falling toward a stellar mass black hole feet first, the gravity pulling on your feet would be enormously stronger than the gravity pulling on your head, because your feet are closer to the singularity by the length of your body. That difference, that tidal gradient, would pull your body along the direction of fall, stretching it. At the same time, because the gravity is pulling everything inward toward a central point, the sides of your body would be squeezed toward each other, compressed horizontally while being stretched vertically. The technical term for these two simultaneous forces is stretching along the radial direction and compression along the transverse directions. The informal term, the one that captures what is actually happening, is spaghettification. You're being drawn out into a thread. Here is the detail that most people find the most disturbing when they first hear it. For a stellar mass black hole, a black hole with a mass of perhaps 10 to 20 times our Sun, spaghettification does not happen inside the event horizon. It happens outside it. The tidal forces at the event horizon of a small black hole are so extreme that they would tear apart any ordinary matter, including a human body, long before that matter ever reached the boundary of no return. If you were falling toward a stellar mass black hole, you would be destroyed thousands of kilometers from the event horizon, not by crossing any threshold, not by hitting any surface, simply by the difference in gravitational pull between one part of your body and another growing beyond what the molecular bonds holding you together can withstand. First you would feel a stretching sensation, a gentle elongation, as if something were pulling your feet and your head in opposite directions. Then that pull would intensify rapidly. The forces would exceed what any biological tissue can tolerate, and then the process would accelerate beyond any analogy I can offer you that would be comfortable to hold in your mind at night. But here is the counterintuitive truth that makes supermassive black holes so different, and in some ways so much more unsettling. For a large enough black hole, the tidal forces at the event horizon are actually quite gentle. The reason comes down to the mathematics of how tidal forces scale with distance and mass. The tidal force you experience depends not just on how strong the gravity is, but on how quickly it changes across the length of your body. For a stellar mass black hole, the event horizon is tiny, just a few kilometers across, so the gravity changes enormously over the span of a human body near it. But for a supermassive black hole with billions of solar masses, the event horizon is billions of kilometers across. At that scale, the difference in gravity between your head and your feet is proportionally tiny, even right at the event horizon. The tidal force at the horizon of a sufficiently large black hole is not just survivable, it is imperceptible. You could cross the event horizon of the black hole at the center of Messier 87, the one 6.5 billion times the mass of our Sun, and feel nothing at all. No stretching, no discomfort, no signal that anything significant had occurred. You would be inside, and you would not know it. And that somehow makes it more terrifying rather than less. Because it means that the ultimate boundary in the universe, the line beyond which nothing returns, is one you can cross in perfect comfort, in complete ignorance, with no warning and no sensation. The danger is not at the threshold. It is beyond it, waiting as you fall deeper, as the singularity draws closer, as the tidal forces that were gentle at the horizon grow stronger with every passing moment. Eventually, at some point between the event horizon and the singularity, the forces will become severe, the stretching will begin, and for a supermassive black hole that point may be far inside, deep within the geometry of a space from which there was never any hope of return. By the time you feel the universe beginning to pull you apart, you have been inside for what may have been hours of your own experienced time. There is something I want to sit with here for a moment. Spaghettification is often described in physics writing with a kind of detached, almost comic tone. The word itself encourages that. But underneath the terminology, what it describes is the universe asserting a kind of absolute physical authority over matter. The molecular bonds that hold atoms together in the particular arrangement that makes you a human being, bonds that have been maintained through every moment of your existence, are simply overridden, not broken by a violent impact, not disrupted by heat or cold or chemical reaction, overcome by the geometry of space-time itself, by the curvature of the universe pulling harder on one part of you than another, until the difference exceeds what matter can endure. It is gravity not as a gentle background force but as a structural dissolver. And yet even this has a strange beauty to it when viewed from the right distance. The matter that is stretched and compressed and ultimately pulled apart does not disappear. It becomes part of the infalling stream of material spiralling toward the singularity. The atoms that made up something complex, something structured, something that once had a specific form and function, are reduced to their most fundamental components and drawn into the most extreme environment the universe contains. In a sense, spaghettification is the universe's way of disassembling complexity at the boundary of its most extreme object. Not destroying, but unmaking. Returning matter to its most elemental state before drawing it across the final threshold. It is violent, yes, it is terrifying, but it is also, in its way, complete. And in the deep quiet of tonight, lying still, thinking about the forces that govern the cosmos, there is something almost clarifying about knowing that even at the most extreme boundary in the universe, the rules still hold. Physics still describes it. The universe is strange, but it is not arbitrary, and that in its own way is a form of comfort. There is a kind of mercy in enormity. It sounds like a contradiction. The larger the black hole, the more mass it contains, the more powerful its gravitational pull across vast distances of space. And yet, paradoxically, the larger the black hole, the gentler its immediate grip on something falling through its event horizon. This is one of the most counterintuitive truths in all of black hole physics, and it is one that I find myself returning to again and again, not just as a scientific fact, but as a kind of strange philosophical comfort. The most monstrous objects in the universe are, in a very specific and precise sense, the kindest ones to fall into. And understanding why that is true will tell you something deep about the nature of gravity itself. We explored this briefly when we talked about spaghettification, but I want to go deeper now because the implications of this fact are more profound than they might first appear. Let us start with the numbers. A stellar mass black hole, one with perhaps 10 times the mass of our Sun, has an event horizon with a radius of roughly 30 kilometers. At that radius, the tidal forces, the difference in gravitational pull between one side of a human body and the other, are catastrophically large. They would tear a person apart many thousands of kilometers before they even reach that boundary. The event horizon of a stellar mass black hole is essentially surrounded by a zone of guaranteed destruction that extends far beyond the horizon itself. Now consider a supermassive black hole. Take Sagittarius A star, the black hole at the center of our own galaxy, with a mass of 4 million solar masses. Its event horizon has a radius of roughly 12 million kilometers. 12 million kilometers. That is about 17 times the radius of our Sun. At that distance from the singularity, the tidal forces on a human body are actually quite mild. Not comfortable exactly, but survivable, below the threshold of spaghettification. You could cross the event horizon of Sagittarius A star without being torn apart, without feeling anything dramatic at all, if you were falling freely. And for the truly colossal black holes, the ones containing billions or tens of billions of solar masses, the tidal forces at the event horizon become so gentle that they would be essentially undetectable by human senses. You would fall through the boundary of no return feeling perfectly normal, weightless, perhaps, in free fall, surrounded by a subtly distorted view of the universe outside, but physically intact, unaware, in any direct sensory way, that you had just crossed the most significant threshold in the cosmos. The mathematics behind this is elegant and worth understanding. Tidal force depends on two things: the strength of gravity at a given distance, and how rapidly that strength changes over the length of the object experiencing it. For a black hole, the event horizon sits at a distance proportional to the black hole's mass. Double the mass, double the radius of the event horizon, but tidal force falls off with the cube of distance. So as the event horizon gets larger with increasing mass, the tidal force at that horizon decreases with the cube of the radius, which itself grows linearly with mass. The net result is that tidal force at the event horizon decreases as the mass of the black hole increases. A black hole 4 times as massive has an event horizon 4 times as large, but the tidal forces there are 64 times weaker. Scale that up to millions or billions of solar masses, and the tidal forces at the horizon become trivially small by any human standard. This creates a situation that is, when you really sit with it, profoundly strange. The black holes most likely to allow a human being to survive the crossing of their event horizon are also the black holes most likely to trap that person for the longest time before the singularity becomes unavoidable. A stellar mass black hole would destroy you before you reach the horizon, so the question of what happens inside is academic for a biological traveller. But a supermassive black hole would let you in gently, intact, experiencing nothing unusual at the moment of crossing, and then give you time, potentially hours of subjective experience, before the inevitable tidal forces deep inside grew strong enough to matter. You would have time to think, time to observe, time to experience the interior of a black hole as a conscious, intact observer, and then, eventually, the universe would collect what it was always going to collect. I want to dwell on what that crossing might actually feel like, experientially. You are falling freely, which means you are in a state of weightlessness. The same weightlessness an astronaut feels in orbit, the same sensation you would have in any freely falling elevator. There is no weight pressing on you in any direction. You drift. Around you, the view of the outside universe is dramatically distorted by lensing. The stars are compressed into a shrinking circle of light behind you, and ahead lies the darkness of the interior. But there is no wall, no barrier, no sensation of crossing anything. The event horizon is not a surface. It is a mathematical boundary defined by the geometry of space-time, and it announces itself to no one. You pass through it the way you pass through the invisible boundary between one country and another on an open plain. Nothing marks it. Nothing signals it. The universe offers you no warning. And here is the detail that I think deserves its own moment of silence. After you cross, you can still see the outside universe, at least for a while. Light from outside can still reach you, because light can fall inward across the event horizon just as you did. You look back, and you see stars, galaxies, the glow of the accretion disk if one exists, the whole brilliant panorama of the cosmos outside. But there is an asymmetry now that is absolute. You can receive light from outside. You cannot send any back. Your situation is perfectly analogous to being able to hear someone speaking to you through a door while being unable to make any sound they can detect. The connection is one way. You are receiving the universe. The universe is no longer receiving you. There is a particular quality to this image that I find almost unbearably poignant. From inside, looking out, you could watch the universe continue. Stars would continue their lives. Galaxies would continue their slow dances. If you could survive long enough inside a truly massive black hole, you might, in principle, receive light signals from events happening billions of years in the future of the outside universe, compressed and blue-shifted as they fall in after you. You would be, in a sense, a witness to the future, receiving its light but unable to participate in it. A passenger behind glass, present and perceiving but unreachable. And yet there is, I think, something almost merciful in that image too. The universe does not close its eyes to you just because you have crossed the horizon. It still sends you its light. It still shows you its stars. It allows you, in those final hours of free fall through the interior of the most extreme object it has ever created, to remain a witness to everything that is happening outside, to keep looking, to keep seeing, to remain until the geometry of space-time finally makes it impossible, an observer of the cosmos. The universe, in its strange and indifferent way, does not abandon you entirely. It simply makes the relationship permanent and one-directional. You belong to the black hole now, but the black hole, in its strange mercy, still lets you watch the stars. You're inside now. The event horizon is behind you, not above you, not below you, not in any direction you can point to. Because inside a black hole, the concept of direction has already begun to change in ways that your intuition was never built to handle. The event horizon is behind you, the way the past is behind you. It is a moment that has already occurred, not a place you could return to if you turned around. You cannot go back to it any more than you can go back to yesterday. It exists in your past now, and everything in your future, every possible path that space-time allows you to take from this moment forward, leads to one place, one moment, the singularity, and it is coming toward you whether you move or not. I want to take a moment to explain what I mean when I say that space and time swap roles inside a black hole, because this is one of the most genuinely disorienting ideas in all of physics, and it deserves to be unpacked carefully. Outside a black hole, you have freedom in space and inevitability in time. You can move in any direction through the 3 dimensions of space. You can go left or right, up or down, forward or backward, but you cannot move through time in any direction other than forward. Time flows one way. That is a constraint you live with every moment of your existence, and it is so fundamental that you rarely think of it as a constraint at all. It simply is. Inside a black hole, something happens to this relationship. The radial direction, the direction pointing toward the singularity, ceases to be a spatial direction in the normal sense. It becomes time-like, inevitable, unidirectional. The singularity is not a place you are falling toward. It is a moment in your future that you cannot avoid, the way you cannot avoid tomorrow, and the 3 remaining directions of space, the ones perpendicular to your fall, become the directions in which you have some freedom of movement. Inside a black hole, you are free to move sideways through what used to be space, but you are being carried inevitably forward through what used to be a direction in space, and is now effectively your future. This swap, this strange inversion of spatial and temporal roles, is not a metaphor. It is a mathematical consequence of the geometry of spacetime inside the event horizon, as described by general relativity. The Schwarzschild solution, the set of equations that describes a non-rotating black hole, shows that inside the horizon the sign of certain terms in the metric, the mathematical object that describes spacetime geometry, flips. What was a spatial dimension becomes timelike. What was timelike remains so, but is now joined by an additional timelike direction pointing inexorably toward the singularity. You're not in space that happens to have a dangerous location in it. You're in a region of spacetime that has a dangerous moment in its future, and that moment is approaching at the rate of 1 second per second, the same rate at which all your moments always approach. So what do you experience in the time between crossing the event horizon and reaching the singularity? For a stellar mass black hole, this question is largely academic because, as we discussed, a human being would be spaghettified before reaching the horizon. But for a supermassive black hole, the interior crossing time can be substantial. For a black hole of a few billion solar masses, the time between crossing the event horizon and reaching the singularity, measured in the infalling observer's own proper time, might be several hours. Hours inside the most extreme environment the universe contains. What would you perceive during those hours? Strangely, perhaps not very much that was immediately alarming. You would be in free fall, weightless. The view of the outside universe would be visible ahead of you, distorted and blue-shifted, the light of the cosmos pouring in across the horizon you just crossed, compressed into a shrinking, brightening patch of light. The interior around you would be dark, not the darkness of space, which is illuminated by distant stars, a deeper darkness, a region with no light sources of its own, lit only by the infalling glow from outside. As you fell deeper, the tidal forces would begin to grow, slowly at first, then with increasing urgency. The difference in gravity between the near side and the far side of your body would begin to be noticeable, then uncomfortable, then severe. At some point before the singularity, spaghettification would begin, even for the gentlest supermassive black holes. The geometry of spacetime near the singularity becomes so violently curved that no configuration of matter can maintain its structure. This is the point at which the physical experience of falling inside a black hole for any material object reaches its terminus. The singularity itself is not a place where you arrive and then something happens to you. The singularity is the end of the coordinate system, the end of the equations, the point where general relativity returns infinities and stops making predictions. What actually happens there, physically, is unknown. Our best theory simply stops describing reality at that point. But here is something that physics does tell us about the approach to the singularity, something subtle and strange and worth sitting with. As you approach it, as the tidal forces grow, you would begin to see the light from the outside universe undergoing a remarkable transformation. The photons falling in from outside are being compressed in time as the singularity approaches. In principle, in the final moments before the singularity, an infalling observer might receive light signals from arbitrarily far into the future of the outside universe, blue-shifted to extreme energies and compressed into a vanishingly brief instant of experienced time. The entire future history of the visible universe, or at least whatever portion of it sends light toward this black hole, might flash by in an instant. Not that you would survive to perceive it coherently, but the physics contains, within its equations, this haunting image of the universe's future arriving all at once at the threshold of its own most extreme object. There is another layer to this interior that I want to add, and it involves the question of what kind of black hole you have fallen into. The Schwarzschild black hole, the non-rotating, uncharged variety, has a single singularity, a point in the future that all infalling observers must reach. But a rotating black hole, described by what physicists call the Kerr solution, has a more complex interior structure. It contains not one but potentially two horizons, an outer event horizon and an inner one called the Cauchy horizon. And the interior of a Kerr black hole is theoretically far stranger than the Schwarzschild interior, containing regions where the singularity is ring-shaped rather than point-like, and where the equations of general relativity raise the theoretical possibility, deeply contested and almost certainly not physically realizable in practice, of paths that avoid the singularity entirely. These exotic solutions are almost certainly destabilized by quantum effects and by the radiation that falls into the black hole, but their mathematical existence hints at how much richer and stranger the interior geometry of a real black hole might be compared to our simplest models. What I want you to take away from all of this is not the technical details, though they are extraordinary. What I want you to feel is the quality of the interior, the silence of it, the inevitability, a place where the normal grammar of space, the idea that you can choose a direction and move toward or away from things, has been quietly revoked, where the future is not open but is a single, specific, unavoidable moment drawing steadily closer, where the outside universe is still visible, still pouring its light inward, but receding from any possibility of contact. There is something almost meditative about that image, when you hold it gently and do not fight it. A space of absolute stillness in a certain sense. A place where the usual anxieties about direction and choice and escape are simply not available. Where the only thing left is the present moment, and then the next present moment, and then the next, each one falling toward its conclusion at exactly the pace that time demands. Inside a black hole, in the end, there is only now, and now, and now, until there is not. Everything I have told you so far about crossing the event horizon rests on one foundational assumption: that general relativity is correct, that space-time curves smoothly at the horizon, that an infalling observer experiences nothing dramatic at the moment of crossing, that the event horizon is gentle, invisible, unmarked. This is what Einstein's equations predict, and for nearly a century physicists accepted it as the most reasonable picture of what crossing a black hole's boundary would actually be like. Then, in 2012, 4 physicists published a paper that threw all of that into question. They argued, using the principles of quantum mechanics, that the event horizon might not be gentle at all, that instead of an invisible, undetectable boundary, the horizon might be a wall of fire, infinite in temperature, lethal the instant you touched it. And the argument they made was so rigorous, so carefully constructed, that the physics community has been wrestling with it ever since. The physicists who proposed this idea were Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully. The paper became known by their initials as the AMPS paper, and the phenomenon it described became known as the firewall paradox. To understand why they proposed it, and why it caused such a disruption, you need to understand a concept from quantum mechanics called entanglement. Quantum entanglement is one of the strangest features of quantum physics, and it is completely real and experimentally verified. When two particles interact in certain ways, they become entangled. Their quantum states are correlated in a way that persists regardless of the distance between them. Measure one particle, and you instantly know something about the other, no matter how far apart they are. Einstein famously called this spooky action at a distance. He was uncomfortable with it, but it is real, and it is fundamental to how the quantum world works. Now, the AMPS argument goes like this. When a black hole forms and begins to slowly radiate, via a process we will explore in the next chapter, the particles it emits are quantumly entangled with the interior of the black hole. This entanglement is necessary to preserve a principle called unitarity, which is essentially the quantum mechanical law that information is never destroyed. The radiation leaving the black hole must carry information about what fell in, and it does this through quantum entanglement with the interior. But here is the problem. Quantum mechanics has its own rule about entanglement, a rule called the monogamy of entanglement. A particle can only be maximally entangled with one other system at a time. It cannot be simultaneously maximally entangled with two different things. It is, in this precise technical sense, faithful. It gives its full quantum correlation to one partner and cannot split that between two. This is where the contradiction bites. For the event horizon to be smooth and undetectable, as general relativity demands, the quantum fields at the horizon must be in a very specific state. They must be entangled with the interior of the black hole. That entanglement is what makes the crossing feel gentle, what prevents any sharp discontinuity at the horizon. But for information to escape in the radiation, that same radiation must be entangled with the previously emitted radiation outside the black hole, carrying the information of what has fallen in. You need the horizon fields to be entangled with the interior for smoothness. You need the outgoing radiation to be entangled with the previously emitted radiation for information preservation. But monogamy of entanglement says you cannot have both. Something has to give, and the AMPS team argued that what gives is the smoothness of the horizon. If information is to be preserved, the entanglement between the horizon and the interior must be broken. And breaking that entanglement, according to the mathematics of quantum field theory and curved spacetime, would release an enormous burst of energy right at the horizon, a wall of high-energy radiation, a firewall, lethal to anything crossing it. The implications of this are staggering, and they branch in every direction. If the firewall is real, then everything we thought we understood about falling into a black hole is wrong. The gentle, invisible crossing is an illusion. The event horizon is not a quiet threshold, but a violent barrier. Any infalling observer, rather than drifting peacefully through an undetectable boundary, would be instantly incinerated the moment they touched the horizon. Burned by a wall of energy so intense, it would be equivalent to every quantum field simultaneously releasing its energy at once. There would be no interior experience to speak of, no hours of free fall through a strange reversed space-time, just the horizon, and then nothing. But if the firewall is not real, if we reject it to preserve the smoothness of the horizon, then information must be destroyed when matter falls into a black hole, and destroying information violates one of the most fundamental principles of quantum mechanics, unitarity, the rule that says the quantum state of a system evolves in a way that is, in principle, reversible. That information is never truly lost, only scrambled. Violating unitarity would not just be an inconvenience for physics, it would require rewriting quantum mechanics at a foundational level. It would mean that the universe itself does not keep track of its own history in the way we thought it did. So the firewall paradox does not offer you a comfortable way out. On one side, you have general relativity's smooth horizon and the destruction of information. On the other side, you have quantum mechanics' demand for information preservation and a wall of fire where the horizon should be. Both options are deeply troubling. Both options require abandoning something that we thought was a cornerstone of physical law. The paradox is not a minor technical puzzle. It is a genuine collision between our two best theories of reality, happening at the most extreme environment the universe offers, and it has not been resolved. As of today, there is no consensus. There are proposals, there are candidate resolutions, there are extraordinary ideas like the ER equals EPR conjecture, which suggests that quantum entanglement between particles is actually equivalent to microscopic wormholes connecting them, and that this connection might thread the firewall problem in a way that preserves both smoothness and information. But none of these proposals has been proven. The firewall sits at the event horizon of our knowledge, as impenetrable in its way as the event horizon of a black hole. I find the firewall paradox one of the most honest things physics has produced in recent decades. It does not pretend that our theories are complete. It does not paper over contradictions. It exposes, with extraordinary precision, the exact point where our understanding of the universe breaks down. And it tells us something important. The universe does not owe us consistency between our theories. General relativity and quantum mechanics were each built to describe different regimes of reality, and they each work brilliantly in their own domain. But at the event horizon of a black hole, those domains collide. And in that collision, the universe is telling us that there is something deeper waiting to be understood. A more fundamental theory, one that contains both relativity and quantum mechanics as special cases, one that can describe the geometry of spacetime and the behavior of quantum fields in a unified language. We do not have that theory yet, but the firewall paradox tells us, with burning clarity, that we need it. And in the dark, lying still, thinking about the edge of human knowledge, that need feels less like a failure and more like an invitation. The universe is asking us to look more deeply, and we are only just beginning to learn how. For most of the 20th century, physicists believed that black holes were permanent, once formed, always present. A black hole that had swallowed a star, a planet, a cloud of gas, would retain that mass indefinitely, holding it behind its event horizon for as long as the universe endured. The logic seemed airtight. Nothing escapes a black hole, therefore a black hole loses nothing, therefore a black hole persists forever. It was a clean, simple, satisfying conclusion. And in 1974, a 32-year-old British physicist named Stephen Hawking proved that it was wrong. What Hawking discovered, through a calculation that combined quantum field theory with the curved spacetime of general relativity, was that black holes are not perfectly black. They radiate, not because anything escapes from inside the event horizon, that remains impossible, but because of something that happens at the horizon itself, at the boundary between the interior and the exterior, due to the strange and counterintuitive behavior of quantum fields in the vacuum of space. Hawking showed that a black hole slowly leaks energy, particle by particle, quantum by quantum, over timescales so vast they dwarf the current age of the universe. But leak it does, and if a black hole leaks energy, it loses mass, and if it loses mass, it shrinks, and if it shrinks long enough, it eventually evaporates entirely. Black holes are not eternal, they die. Slowly, almost unimaginably slowly, but inevitably and completely. To understand how Hawking radiation works, you need to spend a moment with one of the strangest facts about quantum mechanics. The vacuum of space is not empty. This sounds wrong. Vacuum means empty. But in quantum field theory, the vacuum has a rich and active structure. It is filled with what physicists call quantum fluctuations, or virtual particle pairs, pairs of particles and their antiparticles that spontaneously pop into existence from the energy of the vacuum itself, exist for an almost impossibly brief moment, and then annihilate each other and vanish. This process happens constantly, everywhere in space, even in regions containing nothing else at all. The vacuum seethes with these ephemeral pairs, borrowing energy from the quantum uncertainty principle for just long enough to exist before paying it back. Under normal conditions, these virtual pairs always annihilate. They are born together and they die together, leaving no net effect on the world. But near the event horizon of a black hole, something different can happen. A virtual pair forms right at the boundary. One particle of the pair appears just outside the horizon. The other appears just inside it. Before they can find each other and annihilate, the one inside is swept inward by the geometry of spacetime, falling toward the singularity. The one outside, suddenly without a partner to annihilate with, becomes real. It exists. It carries energy borrowed from the vacuum, and that energy has to come from somewhere. It comes from the black hole itself. The infalling particle effectively carries negative energy into the black hole, reducing its mass by a tiny, tiny amount. The outgoing particle flies away as real radiation, as a real photon or a real electron, or whatever particle type the quantum fluctuation produced. This is Hawking radiation, and its net effect, accumulated over inconceivable spans of time, is the slow evaporation of the black hole. The temperature of Hawking radiation is inversely proportional to the mass of the black hole. A more massive black hole radiates at a lower temperature. A stellar mass black hole, one with 10 times the mass of our Sun, has a Hawking temperature of roughly 60 billionths of a degree above absolute zero. That is an almost incomprehensibly cold temperature. The cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space, has a temperature of about 2.7 degrees above absolute zero. That background radiation is billions of times hotter than the Hawking radiation from a stellar mass black hole, which means that a black hole of that size is actually absorbing more energy from the cosmic background than it is emitting as Hawking radiation. It is, in net terms, gaining mass, not losing it. For Hawking radiation to dominate, for a black hole to be in net decline, the cosmic background radiation would first have to cool below the black hole's Hawking temperature. This will happen as the universe expands and the background cools, but not for an almost unimaginable span of time. For a stellar mass black hole to evaporate completely through Hawking radiation alone, the time required is roughly 10 to the power of 67 years. Write that out as a number, and it is a 1 followed by 67 zeros. The current age of the universe is approximately 13.8 billion years, 13.8 times 10 to the power of 9 years. The evaporation timescale of a stellar mass black hole is longer than the age of the universe by a factor so large that comparing them feels almost absurd. For a supermassive black hole of 1 billion solar masses, the evaporation time stretches to something like 10 to the power of 99 years. A number so vast that it makes the evaporation time of a stellar mass black hole look brief by comparison. These are not timescales that have any meaning in human terms. They are timescales on which galaxies are long dead, on which the last stars have burned out, on which the universe has entered a cold, dark, diffuse state, almost incomprehensibly different from what we see tonight. But here is what matters physically. The evaporation does happen, and as a black hole loses mass, its Hawking temperature rises. A smaller black hole is hotter. This creates a feedback effect. As the black hole shrinks, it radiates more intensely, which causes it to shrink faster, which raises the temperature further, which increases the radiation further. The evaporation accelerates over time. In the final moments of a black hole's life, this process reaches an extraordinary crescendo. The black hole, now reduced to a tiny fraction of its original mass, radiates at an increasing rate, its temperature climbing toward extreme values, until in a final burst of energy it completes its evaporation entirely. What remains? According to our current best understanding, nothing. The black hole is gone. The event horizon, the singularity, the warped space-time, all of it, dissipated into a burst of radiation spreading outward at the speed of light. The most permanent-seeming object in the universe ends not with a collapse, but with a glow. Stephen Hawking published this result in 1974, and it was met initially with skepticism. The idea that black holes radiated seemed to contradict everything that had just been established about them. Hawking had to fight to be heard. But as physicists examined the calculation, they found it to be rigorous, elegant, and deeply connected to fundamental principles of both quantum mechanics and thermodynamics. It established that black holes have a temperature, that they have an entropy, that they are thermodynamic objects subject to the same laws as everything else in the universe, and it opened the door to the information paradox, the question of what happens to all the information that fell into the black hole if the black hole ultimately evaporates completely, leaving behind only thermal radiation that carries no specific information about what was consumed. That paradox lives at the heart of modern theoretical physics, and it begins here, with a quiet discovery made by a young physicist in Cambridge, sitting with equations that told him the universe's most fearsome objects are, in the end, not eternal after all. They shine, they dwindle, and they vanish, like everything else in this vast, beautiful temporary cosmos. I want you to think about what makes you you, not in a philosophical sense, not your memories or your personality or your sense of self, though those matter enormously in human terms. I mean in a purely physical sense. What makes you you is the precise arrangement of the atoms that constitute your body, the specific sequence of base pairs in your DNA, the exact configuration of neurons in your brain, the particular pattern of connections between them that encodes everything you have ever learned and felt and remembered, the precise quantum state of every particle in your body at this moment. All of that information, that almost incomprehensible specificity of arrangement, is what distinguishes you from any other collection of atoms in the universe. It is, in the most literal physical sense, what you are. And the question at the heart of the information paradox is this. If you fell into a black hole and the black hole eventually evaporated, would any of that information survive? Or would the universe simply forget that you ever existed? In quantum mechanics, information is sacred. This is not a metaphor or an overstatement. The principle of unitarity, one of the foundational pillars of quantum theory, states that the complete quantum information describing a physical system is always conserved. It can be transformed. It can be scrambled beyond any practical hope of recovery. But it cannot be destroyed. The quantum state of a system evolves according to equations that are, in principle, reversible. If you knew the complete quantum state of the universe right now, you could in principle run the equations backward and reconstruct the complete quantum state of the universe at any point in the past. Every event that has ever happened leaves an indelible imprint on the quantum state of the universe. Nothing is truly erased. This principle is so fundamental to quantum mechanics that violating it would not just be inconvenient, it would require rebuilding the theory from the ground up, and yet black holes appear to violate it. Here is the problem in its starkest form. You fall into a black hole. The black hole, over an almost incomprehensible span of time, evaporates through Hawking radiation. That radiation, according to Hawking's original calculation, is perfectly thermal. It is random. It carries no specific information about what fell in. It is, in quantum mechanical terms, a mixed state, one that is identical regardless of whether the black hole originally swallowed you, or a star, or a cloud of hydrogen gas, or a library of books. All of those inputs produce, according to the original Hawking calculation, the same featureless thermal output. The information about what went in is not in the radiation that comes out. When the black hole finishes evaporating, the radiation has dispersed into the universe, and the information is gone, not scrambled, not hidden, gone, destroyed. Which is precisely what quantum mechanics says cannot happen. This is the information paradox, and it is not a minor technical difficulty. Stephen Hawking himself, after proposing the radiation that bears his name, spent decades arguing that information genuinely was destroyed in black holes, that quantum mechanics, at least in its standard form, simply did not apply inside the event horizon, that black holes were genuine information destroyers, and that physics would have to accommodate this fact. It was a bold position, and it put him in direct conflict with a large part of the theoretical physics community, particularly those working on string theory and related approaches, who were convinced that information could not be destroyed, and that Hawking's radiation must somehow, in ways not yet understood, carry the information out encoded in subtle quantum correlations. The debate came to a head in a famous scientific wager. In 1997, Hawking and the physicist Kip Thorne bet against John Preskill that information was destroyed in black holes. The stakes were an encyclopedia of the winner's choice. It was a bet that would not be settled for years, and it was settled not by a single decisive calculation, but by a gradual accumulation of theoretical evidence pointing in one direction. In 2004, Hawking conceded the bet. He announced that he had found a way to understand how information could escape from a black hole encoded in the Hawking radiation, through subtle quantum correlations that his original calculation had not captured. He presented Preskill with a baseball encyclopedia, chosen because information could be retrieved from it. Though Preskill noted it might have been more appropriate to receive the information in a more usable form, Thorne did not concede, and the question of exactly how information escapes, if it does, remains one of the deepest open problems in theoretical physics. The leading modern approach to resolving the paradox comes from a result known as the Page curve. In 1993, physicist Don Page showed that if information is preserved, the entropy of the Hawking radiation should follow a specific pattern over time. It should rise as the black hole evaporates, reach a maximum at the halfway point of the evaporation, and then decrease back towards zero as the black hole completes its evaporation, with the final state of the radiation being a pure quantum state, encoding all the original information. This curve, the Page curve, is a prediction of what unitarity-preserving evaporation should look like, and in recent years, remarkable calculations using techniques from string theory and quantum gravity have shown that the entropy of Hawking radiation does indeed seem to follow the Page curve, suggesting that information is preserved. The calculations are technically extraordinary, involving concepts like quantum extremal surfaces and the island formula, and they represent some of the most sophisticated work in theoretical physics of the past decade. But they do not yet provide a complete, satisfying picture of the mechanism. They tell us that information must come out. They do not yet fully explain how, And here is the aspect of the information paradox that I find most quietly haunting when I think about it in the context of tonight's journey. If information is preserved, then in principle, everything that has ever fallen into a black hole is still encoded somewhere in the universe. Not inside the black hole, but in the radiation it has emitted, scrambled to a degree that is, for all practical purposes, absolutely irretrievable, but present. In principle, if you had access to all the Hawking radiation ever emitted by a black hole, and if you had a quantum computer of unbounded power, and if you understood the exact mechanism of information encoding, you could reconstruct what fell in. Every star, every planet, every atom of every person or object that ever crossed the event horizon. All of it is still there, in some sense, encoded in the thermal glow of a dying black hole, spread across the universe in a pattern of quantum correlations of such staggering complexity that no civilization will ever practically decode it. But not gone. Never truly gone. There is something about that idea that I find simultaneously terrifying and deeply comforting. Terrifying because it means the universe maintains a record of everything, keeps a kind of cosmic ledger of every event that has ever occurred, at a level of detail and permanence that goes far beyond anything we can access or influence. Comforting because it means that nothing is truly lost, that the universe does not forget, that the information making up every person, every moment, every experience, persists in some form, encoded in the fabric of physical reality, long after the original form has dissolved. You are made of information. And information, the universe insists, cannot be destroyed. It can only be transformed, dispersed, hidden, but never erased. And in the quiet of tonight, with the stars outside and the dark all around, that feels like something worth holding on to. There is a monster at the centre of our galaxy. Not a metaphorical monster, not a dangerous region of space or a dense cluster of stars. An actual black hole, 4 million times the mass of our Sun, sitting 26,000 light-years from where you're lying right now, quietly governing the gravitational architecture of the entire Milky Way. Every star in our galaxy, all 200 to 400 billion of them, orbits the centre of the galaxy, and at that centre, anchoring everything, warping the space around it across thousands of light-years, sits Sagittarius A star. It has been there for billions of years. It will be there for billions more, and tonight, as you lie in the dark, it is there. Patient, massive, waiting. The name Sagittarius A star refers to a compact radio source at the centre of the Milky Way, located in the direction of the constellation Sagittarius as seen from Earth. Astronomers first detected unusual radio emissions from this region in 1974, though the nature of the source was debated for years. Over the following decades, as telescope technology improved and infrared observations allowed astronomers to peer through the dense clouds of gas and dust that obscure the galactic centre, the evidence for a supermassive black hole at that location accumulated steadily and compellingly. The key evidence came from tracking the orbits of individual stars near the galactic centre, stars that, for no apparent reason, were moving extraordinarily fast, stars carving tight elliptical orbits around an invisible point, orbits so fast and so tightly curved that only one explanation fit the data. One star in particular, designated S2, became the centrepiece of this story. S2 orbits Sagittarius A star with a period of roughly 16 years. 16 years. In cosmic terms, that is extraordinarily short. Our own Sun takes approximately 230 million years to complete one orbit around the galactic centre. S2 completes its orbit around the central black hole in 16 years, tracing an ellipse that brings it as close as 120 astronomical units from the black hole at its nearest point. 120 astronomical units is roughly the distance from our Sun to the beginning of the outer solar system. S2 passes that close to a 4 million solar mass black hole every 16 years, and at its closest approach, it travels at approximately 3% of the speed of light. 3% of the speed of light, 9,000 kilometers per second. That is not a number that belongs in any human frame of reference. It is a cosmic speed, achieved because the gravitational pull of 4 million solar masses is accelerating this star to extraordinary velocities on every pass. By tracking S2 and dozens of other stars in this region over many years, two independent teams of astronomers, one led by Reinhard Genzel at the Max Planck Institute in Germany and one led by Andrea Ghez at UCLA precisely measured the mass and position of Sagittarius A star. Their results agreed: 4 million solar masses, contained within a region smaller than our solar system. No other known object could produce that combination of mass and compactness except a black hole. In 2020, Genzel and Giers shared the Nobel Prize in Physics for this work. The citation read, "For the discovery of a supermassive compact object at the centre of our galaxy." It was, in the careful language of physics, a polite way of saying, "We have found the black hole at the heart of the Milky Way, and we have proven it beyond any reasonable doubt." And then, in 2022, came something that no astronomer alive had dared to fully expect: the Event Horizon Telescope collaboration, the same global network of radio telescopes that had imaged the black hole in Messier 87 in 2019, released the first direct image of Sagittarius A star. A ring of glowing orange light, the superheated gas of an accretion disk swirling around the central darkness, captured across 26,000 light-years by a telescope effectively the size of the Earth. The image was blurry by everyday standards, and razor-sharp by any measure of what it represents. You're looking at the shadow of a 4 million solar mass black hole at the centre of your own galaxy. You're seeing, for the first time in human history, the darkness at the heart of the Milky Way. The image of Sagittarius A star was technically more challenging to produce than the earlier image of Messier 87's central black hole, despite the fact that Sagittarius A star is much closer to us. The reason is that Sagittarius A star is also much smaller. Its event horizon, while spanning roughly 12 million kilometers in absolute terms, subtends a tiny angle on the sky because of its distance, and the gas swirling around it moves so fast, completing orbits in minutes rather than the days or weeks it takes to orbit the far more massive Messier 87 black hole, that the accretion disk was flickering and changing shape faster than the telescope could capture a clean image. The team had to develop new algorithms to average out this variability and extract a stable image from the churning data. The result, released after years of careful analysis, matched the predictions of general relativity with extraordinary precision. Einstein's equations, written more than a century ago, describe the shadow of a black hole 26,000 light-years away to within the measurement errors of the best radio telescope array humanity has ever built. Now, I want to sit with the proximity of this for a moment, because there is something different about knowing that the black hole in tonight's story is not in some distant galaxy hundreds of millions of light-years away. It is in our galaxy. It is, by cosmic standards, our black hole. The stars orbiting it are our galactic neighbours, and while 26,000 light-years is an inconceivable distance in human terms, in galactic terms it is the distance to the centre of the city you live in. We are in the outer suburbs of the Milky Way, and at the city centre sits this object. This 4 million solar mass gravitational anchor that has been shaping the structure of our galaxy since before our Sun existed. Is it dangerous to us? Not in any immediate or foreseeable sense. The gravitational influence of Sagittarius A star at our distance is negligible. Our Sun orbits the galactic centre the way a planet orbits a star, and the perturbation from the central black hole at this distance is no more threatening than the general background of galactic gravity we have always lived within. The danger, such as it is, exists only near the galactic centre itself, where stars are densely packed and the tidal forces of the black hole are significant. At 26,000 light-years, we are safe. But safe is not the same as separate. We are gravitationally bound to Sagittarius A star in the same way that Earth is gravitationally bound to the Sun. It holds us. It has always held us. Every orbit our Sun has ever completed around the galactic centre has been an orbit around that black hole. In a very real sense, Sagittarius A star is not just a distant curiosity. It is the gravitational foundation of everything we have ever known. The quiet centre around which our entire cosmic home has been turning for 4.5 billion years. And tonight, it is still there, 26,000 light-years away, in the direction of Sagittarius, turning slowly in the dark. On the 10th of April, 2019, at simultaneous press conferences held in Washington, Brussels, Santiago, Shanghai, Taipei, and Tokyo, a group of scientists unveiled something that had never existed before in the entire history of our species. An image, a photograph, blurry and orange and ringed with light, of a black hole. The first direct visual evidence of an object that had been theorized for over a century. The first time human eyes had ever seen the shadow of a place from which nothing returns. Several of the scientists at those press conferences were visibly emotional. Some had tears in their eyes. And when you understand what it took to produce that image and what the image actually shows, that emotion makes complete and total sense. The black hole in the image is not Sagittarius A star, our own galactic center black hole, though that image would come later. The 2019 image is of the black hole at the center of a galaxy called Messier 87, or M87, a massive elliptical galaxy in the Virgo cluster of galaxies, approximately 55 million light-years from Earth. The black hole at its center has a mass of 6.5 billion solar masses, 6.5 billion times the mass of our Sun. Its event horizon is so large that the entire solar system, from the Sun out to the orbit of Neptune and beyond, would fit comfortably inside it. It is one of the most massive black holes we know of in the observable universe, and it sits at the center of a galaxy that has been observed and catalogued since the 18th century, when the French astronomer Charles Messier listed it as the 87th fuzzy object in his catalogue of things that were not comets. To photograph something 55 million light-years away, something whose shadow subtends an angle on the sky, roughly equivalent to the size of a donut on the surface of the Moon as seen from Earth, required a telescope of extraordinary resolution. No single telescope on Earth could achieve it. The solution was breathtaking in its ambition. The Event Horizon Telescope collaboration linked together 8 radio telescope facilities spread across 4 continents, from Hawaii to Chile to Spain to the South Pole, and synchronized them using atomic clocks accurate to within a fraction of a nanosecond. By combining their data using a technique called very long baseline interferometry, the collaboration effectively created a virtual telescope with a diameter equal to the diameter of the Earth itself, about 12,700 kilometers across, the largest telescope ever assembled, and the resolution it achieved was equivalent to being able to read a newspaper in New York from a cafe in Paris. The data collected by these 8 facilities during observation runs in April 2017 filled hard drives with petabytes of information, so much data that it could not be transmitted over the internet fast enough. The hard drives from the South Pole Telescope had to wait months for the Antarctic winter to end before they could be physically flown out and shipped to the processing centers. All that data then had to be painstakingly correlated, calibrated, and processed by teams of scientists using specially developed algorithms, a process that took nearly 2 years. One of the key figures in developing the imaging algorithms was a young researcher named Katie Booman, whose work helped transform the raw interference data into the image the world eventually saw. When the image was finally produced internally and confirmed to match the predictions of general relativity, the scientists who had spent years working toward that moment experienced something that is rarely described in scientific papers: pure stunned disbelief that it had actually worked. So what does the image actually show? At its center is a dark region, the black hole's shadow. This is not the event horizon itself, though the event horizon lies within it. The shadow is larger than the event horizon because of the way gravity bends light around the black hole. Photons coming from behind and around the black hole are deflected into curved paths, and the region of sky from which no photons can reach your eye. The shadow is larger than the event horizon by a factor of about 2.6. What surrounds the shadow is a bright, asymmetric ring of light. This ring is the glow of superheated gas in the accretion disk, light that has been bent by the black hole's gravity into a ring shape as it travels toward the observer. The ring is brighter on one side than the other. The southern side of the ring is significantly brighter than the northern side in the M87 image. This asymmetry is caused by relativistic beaming. The gas in the accretion disk is orbiting the black hole at a significant fraction of the speed of light, and the side moving toward us has its emission boosted and brightened, while the side moving away is dimmed. The specific pattern of brightness around the ring encodes information about the spin and orientation of the black hole. The image matched the predictions of general relativity with remarkable fidelity. The size of the shadow, the brightness and symmetry of the ring, the overall structure, all of it fell within the range that Einstein's equations had predicted for a black hole of this mass and distance. Scientists had been making these predictions for decades, running simulations of what a black hole image should look like based on general relativity. And when the real image arrived, it looked like the simulations. Not approximately, not vaguely. It looked like them with a precision that confirmed, yet again, that a theory written in 1915 by a patent clerk in Bern, a theory built on pure mathematical reasoning about the geometry of space-time, accurately describes the behavior of matter and light around a 6.5 billion solar mass object 55 million light-years away. The universe, it turns out, is remarkably consistent. 3 years later, in 2022, the Event Horizon Telescope collaboration released a second image, this time of Sagittarius A star, our own galactic black hole. The image showed the same basic structure, a dark shadow surrounded by a bright asymmetric ring of light. Smaller in absolute terms than the M87 image, because Sagittarius A star is far less massive, but similar in angular size on the sky, because it is also far closer. Seeing that image felt different from the M87 image in a way that is hard to articulate but easy to feel, because this was not a distant object in another galaxy. This was ours. This was the dark heart of the Milky Way, the gravitational anchor of our cosmic home, photographed for the first time. A fuzzy orange ring in the direction of Sagittarius, telling us in the clearest possible way that what we had theorized, what we had calculated, what we had suspected for decades, was real. I want to close this chapter with a thought about what these images represent beyond their scientific content. For all of human history, black holes were theoretical objects, mathematical solutions, things that the equations implied existed but that no one had ever seen. They lived in the imagination, in science fiction, in the chalkboard calculations of physicists. And then, in the space of 3 years, we saw 2 of them. We took their portraits. We compared those portraits to the predictions of a century-old theory, and found agreement that bordered on the astonishing. We went from conjecture to confirmation in a single human generation. And what the images show, at their most fundamental level, is a darkness surrounded by light, the most extreme object in the universe, making itself known to us not by what it emits, but by what it holds back. A shadow that tells us everything. A darkness that, in the end, revealed more about the nature of reality than almost anything else we have ever pointed a telescope at. That feels, to me, like something worth staying awake for. There is a question that sits quietly at the back of the mind once you have spent enough time thinking about black holes. We have talked about their formation, their structure, their event horizons and their tidal forces and their patient, almost geological permanence. We have talked about them as objects to study, to image, to theorize about. But at some point, almost inevitably, the question becomes personal. Could one of these things ever come for us? Not in the abstract sense of the universe's long-term fate, but in the immediate practical human sense. Is there a black hole out there, somewhere in the dark between the stars, moving in our direction? And if there were, would we know? The answers are more nuanced, and in some ways more unsettling than a simple yes or no can capture. Let us start with the most immediate concern, the black hole we already know about. Sagittarius A star, 4 million solar masses, 26,000 light-years away. Could it ever pose a direct threat to our solar system? The honest answer is no, not in any astronomically foreseeable future, and not in the way most people imagine. A black hole does not reach out and grab things. It does not have a longer gravitational range than any other object of the same mass. If you replace Sagittarius A star with 4 million solar masses worth of ordinary stars spread across the same region of space, the gravitational effect on our solar system would be essentially identical. The black hole at the galactic center does not pull on us more than the general gravity of the galactic center region already does. We orbit the galactic center the way Earth orbits the Sun, and that orbit is stable on timescales of billions of years. Sagittarius A star is not a vacuum cleaner expanding its reach across the galaxy. It is a gravitational anchor, and we are one of the billions of objects in stable orbit around it. But the Milky Way galaxy is not alone in space. It is gravitationally bound to the Andromeda Galaxy, our nearest large galactic neighbour, currently about 2.5 million light-years away. And Andromeda is moving toward us. At roughly 110 kilometers per second, the two galaxies are on a collision course. In approximately 4.5 billion years, the Milky Way and Andromeda will begin to merge. This is not a catastrophic event in the sense of individual stars colliding. because the space between stars is so vast that direct stellar collisions will be extremely rare. But it is a profound restructuring of the gravitational landscape of our cosmic neighbourhood. The two galactic centres, each with their supermassive black holes, will swing around each other in a gravitational dance, eventually merging into a single, larger elliptical galaxy. And when those two supermassive black holes merge, they will form a single black hole of combined mass, somewhere around 80 to 160 million solar masses, releasing energy in the form of gravitational waves on a scale that dwarfs anything we have ever detected. What does this mean for our Sun and its planets? Probably very little in the immediate sense. The merger of two galaxies is a process that unfolds over billions of years. Individual solar systems ride out these large-scale restructurings the way ships ride out an ocean current, moved by the large-scale flow but largely undisturbed by it in their immediate surroundings. Our Sun might be flung into a different orbit around the merged galactic centre. It might end up much closer to the combined supermassive black hole than it is today, or much farther away. Simulations of the Milky Way-Andromeda merger suggest that our solar system has only a small chance of being ejected entirely from the merged galaxy into intergalactic space, and an even smaller chance of coming close enough to either black hole to be significantly disrupted. The merger is real. The timescale is billions of years, and by the time it happens, our Sun will itself be approaching the end of its main sequence life. Then there is the question of rogue black holes. Stellar mass black holes, born from the deaths of massive stars, are estimated to number in the hundreds of millions within the Milky Way alone. Most of them are invisible. They emit no light. They have no accretion disks. They drift through the galaxy in silence, their presence betrayable only by the subtle gravitational lensing of light from background stars, or by the rare event of passing close enough to another star to begin drawing material from it. Could one of these rogue black holes be on a trajectory that brings it close to our solar system? In principle, yes. In practice, the probability in any given human lifetime or even any given geological era is extraordinarily small. The galaxy is enormous. Even with hundreds of millions of black holes, the average distance between stars is so vast that close encounters are vanishingly rare events. The closest known black hole to our solar system was long thought to be a system called V404 Cygni, roughly 8,000 light-years away. But in recent years, astronomers have identified candidate black holes significantly closer. In 2022, a team using data from the Gaia Space Telescope identified what appeared to be a black hole roughly 1,500 light-years from Earth in the constellation Ophiuchus, dubbed Gaia BH1. Subsequent searches have found additional candidates at similar distances. 1,500 light-years is still an enormous distance. Light from that black hole, if it emitted any, would take 1,500 years to reach your eyes. At any speed, a rogue black hole could realistically be moving through the galaxy. It would take millions of years to cover that distance. We are not in any danger from any known black hole. But the existence of these nearby candidates is a reminder that the dark between the stars is not as empty as it looks. There are invisible objects out there, objects we can only detect when they happen to pass in front of a background star and briefly bend its light. A galaxy full of dark and silent remnants, moving through the night. And there is one more cosmic scenario worth mentioning, one that operates on truly vast timescales. In the extremely long-term future of the universe, as stars exhaust their fuel and stellar formation ceases, as galaxies lose their structure and spread into diffuse halos of cold remnants, the objects that will persist longest are black holes. White dwarfs and neutron stars will eventually cool and fade over timescales of trillions of years. But black holes, even accounting for Hawking radiation, will persist for timescales ranging from 10 to the power of 67 years, for stellar mass black holes to 10 to the power of 99 years for the largest supermassive ones. In the very far future of a cold, dark universe, black holes will be among the last significant structures remaining, the universe's final inheritors, slowly evaporating over incomprehensible spans of time into a thin wash of radiation, the last whisper of all the matter and energy that ever existed. So could a black hole ever reach us? In the immediate future, almost certainly not. In the medium-term future of billions of years, the merger of our galaxy with Andromeda will bring our solar system into a different relationship with the supermassive black holes at each galactic center, though direct harm remains improbable. In the far future, on timescales that dwarf the current age of the universe, black holes will outlast everything else, persisting in a cold and empty cosmos long after every star has burned out and every planet has dissolved. We are not in danger tonight, but we live in a galaxy that is full of darkness and full of these patient, permanent objects, and there is something clarifying about knowing that. Something that puts the small anxieties of a human night into a perspective so vast it becomes, strangely, a comfort. The universe is ancient, its processes are slow, and tonight, beneath all that dark and all those stars, we are exactly where we have always been, safe, small, and utterly surrounded by the extraordinary. We have fallen a long way tonight, together. From the first cold hook of what a black hole actually is, through the violent death of massive stars, through the invisible threshold of the event horizon and the strange mercy of supermassive giants, through the breaking of time and the stretching of matter and the quantum fire that may or may not burn at the boundary of the unknown, we have visited the monster at the heart of our own galaxy. We have looked at the first photograph ever taken of a black hole, that orange ring of light around an absolute darkness 55 million light-years away. We have sat with the information paradox and the firewall and the slow, patient evaporation of the universe's most permanent objects. And now, in this final chapter, I want to pull all the way back, as far back as perspective allows, and ask what all of it means. Black holes are the universe's most extreme objects, the places where gravity wins absolutely, where matter loses its identity, where time loses its direction, where space loses its freedom. They are the endpoints of stellar evolution and the anchors of galactic structure. They are the site of the deepest unsolved problems in theoretical physics, the places where our two greatest theories of reality, general relativity and quantum mechanics, meet and contradict each other in ways we do not yet know how to resolve. They are, in every measurable sense, the most fundamentally challenging things the universe contains. And yet, here is what I keep coming back to. Here is the thing that stays with me when I think about all of this in the quiet of the night. Black holes do not just destroy, they reveal. Every question a black hole raises, every paradox it generates, every contradiction it exposes, is a door, not a wall. A door into a deeper understanding of what reality actually is. Think about what black holes have already taught us. They gave us the first rigorous test of general relativity, in its most extreme regime. The orbits of stars around Sagittarius A star, confirming a mass of 4 million solar masses in a region smaller than our solar system, are a triumph of Einstein's equations in conditions he never imagined they would be tested in. The image of M87's black hole, that orange ring matching the predictions of a century-old theory to within measurement error, is one of the most extraordinary confirmations of a scientific theory in history. Hawking radiation, even though it has not yet been directly detected, connected black holes to thermodynamics and quantum mechanics in ways that transformed our understanding of both. The information paradox has driven decades of theoretical work, producing the holographic principle, string theory insights, the island formula, approaches to quantum gravity that would never have been developed without the pressure of this specific problem to solve. Black holes are not just objects of terror, they are instruments of understanding, and there is something deeper here that I want to name, something about what it means that we, as a species, have been able to figure any of this out at all. Consider the improbability of the situation. We live on a small rocky planet orbiting an average star in the outer suburbs of a mid-sized spiral galaxy. We have existed as a technological civilization for the blink of a cosmic eye. We have no direct access to black holes. We cannot send a probe to one and have it return. We cannot experiment on one in a laboratory. We can only observe them from afar, collect the light and radio waves and gravitational waves they send or influence, and reason about them using mathematics. And yet, using that indirect method, using nothing but light and mathematics and the disciplined application of human curiosity, we have mapped the geometry of space-time near these objects. We have photographed their shadows from 55 million light-years away. We have predicted and detected the gravitational waves produced when two black holes merge, ripples in the fabric of space-time passing through us at the speed of light, stretching and compressing the distance between every atom in your body by a fraction smaller than a proton. We have reached with our minds, into the most extreme corners of the universe. That is not a small thing. That is perhaps the most remarkable thing our species has ever done. Here is the thing most people do not realize when they think about the scale of the cosmos. The scale does not diminish us. I know it can feel that way. 100 million stellar mass black holes in our galaxy alone. Supermassive black holes containing billions of solar masses, event horizons larger than our entire solar system. Timescales measured in numbers with 60 or 90 or 100 zeros. Looking at all of that, it is tempting to feel small, irrelevant, lost. But consider what it takes to know any of that. It takes a mind, it takes curiosity, and language, and mathematics, and the ability to imagine something you have never seen, and then find a way to test whether your imagination was correct. The universe has been producing black holes for billions of years. Black holes have never, as far as we know, wondered what they are. They do not ask questions, they do not build telescopes, they do not lie awake at night feeling the weight of the scale of things and reaching out through that feeling toward understanding. We do, you do, right now, in the dark. We are the universe noticing itself. That phrase has been used before, and I use it again tonight not because it is new, but because it is true, and because nothing I have come across in all of the science we have explored together captures the situation more precisely. The matter that makes up your body was forged in the hearts of stars that lived and died billions of years ago. The carbon and oxygen and nitrogen and iron in your cells were produced by stellar nucleosynthesis and distributed across space by stellar winds and supernova. The same cataclysmic deaths that leave black holes behind. You are made of the same stuff as the universe, and you are, uniquely, the part of that stuff that has become self-aware. The part that can look up at the night sky and ask what is out there. The part that can build a telescope the size of the Earth and point it at a galaxy 55 million light years away and see the shadow of a black hole and understand in some measure what it means. The universe spent 13.8 billion years assembling the conditions for that moment of understanding. And you are its instrument. What do black holes mean for how we live? I think they offer something unexpected. Not terror, though they are terrifying. Not despair, though they swallow everything. They offer perspective. The specific, clarifying perspective of knowing that we exist in a universe of almost incomprehensible scale and depth and strangeness, that the rules governing reality are far more extraordinary than our daily experience suggests, and that we are, nevertheless, here. Thinking, questioning, wondering. Whatever keeps you awake at night, whatever weighs on you in the small hours before sleep, exists alongside all of this. The black holes and the dying stars and the event horizons and the paradoxes, it all coexists. And somehow, knowing the scale of what surrounds us makes the immediate feel both smaller and more precious at once. Smaller because it is. More precious because we are. Thank you for joining me tonight. Truly. These journeys into the deep are only worth taking in company, and you have been extraordinary company through every chapter of this one. If tonight left you with a sense of wonder, or a question you did not have before, or simply a feeling of being briefly connected to something vast and strange and beautiful, then we did exactly what we set out to do. If you enjoyed spending the night falling into the universe's most extreme object, please take a moment to like this and subscribe. It is a small thing, but it keeps this channel alive and lets us keep making these journeys together. And now, as the night deepens around you, let your body be still. Let your breathing slow. Let the questions we have opened tonight settle gently, like dust after a long fall into the quiet of your resting mind. The next time you look up at the night sky,